Okay, AP Physics. We are going to start working with Gauss's law today. Um, so it's just so funny I'm teaching this online. Gauss's law is a little complex. It was developed by a German mathematician who was also a physicist named Friedrich, I don't know, Gauss. Right around the year, this isn't exact, but right around the year 1800, around the turn of that century. And so he was a brilliant mathematician, as a side note. If you ever, if you're bored on quarantine and want to look at what he did a whole lot for that field. But for us, he came up with Gauss's law, which is what we're studying right now. And so he is the one who relates flux, which is what you've been working on in the first part of this chapter, to charge enclosed. Now, what is charge enclosed by? It's enclosed by a hypothetical surface. We just draw shapes, so they're not really there. We just draw these shapes around charges, and the shapes that we draw depend on the type of charge we have. That will make some more sense as I get through it. And so these shapes, when we draw them, we call them Gaussian surfaces. So they're not really there. They're just sort of like invisible shapes containing something. Okay, so he is relating the flux, which is that electric field piercing a surface, again, the surface being this hypothetical shape, to the charge that is enclosed by the surface. And so this is the equation right here for Gauss's law. It says epsilon naught. Epsilon naught is a constant. You saw it when we were doing forces and fields. You didn't really use it. It's called the permittivity constant. It is equal to, it's got a ton of units on the back end of it, but 8.85 times 10 to the negative 12. Coulomb squared divided by newtons times meter squared. But anyways, it's just a constant, so it would be something that's given to you. So we say the net flux through a surface is related directly to the charge enclosed by that surface. You just multiply it by epsilon naught. The calculus way you will see that same thing written is like this. So we put in that calculus definition for flux. Now, when we're actually using it mathematically as an equation, we're going to do this. Epsilon naught times flux, which we already said. And now I'm really simplifying this, right? So this is assuming that the field is perpendicular to the surface. But this is what we were using to find flux in this first year level. So epsilon naught times E times A is equal to Q enclosed. So this little, I'm going to put a little asterisk here. This little equation is a bit of a lie because I'm really, really simplifying the notation of this. But for our intents and purposes, what we do in a first year calculus-based physics course is we use this equation. So in terms of like getting an answer, this is what you're going to do. Okay, so the book gives an example. It looks a little strange. I like really put all the details of it into your PowerPoint. They have two charges, a positive and a negative charge. And they enclose it with 4 different Gaussian surfaces. They just make up 4 different shapes. So here's one shape, right? Here's another shape. Here's a third shape. And here's a fourth shape. Okay, so again, you just can make any shape a Gaussian surface. So I have 4 different Gaussian surfaces. If I draw electric field lines, let me grab a different color here. If I draw electric field lines from these charges, this is positive charge, so field lines go out from positive charges. I'm just kind of drawing it all the way through each surface, okay, something like that. And then the second charge is a negative charge, so field lines go into negative charges. Okay, something like that. This is a bit of a mess. Now there's, again, a much nicer visual in your textbook and in the PowerPoint if you follow along. So they label these different Gaussian surfaces and they look at each one of them. This surface right here, this top black circle, there would be some field lines kind of from the blue perhaps piercing it that you can't see. But there are field lines more piercing out of this surface than in. When field lines are piercing out, remember we call that a positive flux. When they're piercing in, we call that a negative flux. So overall, for this surface, I have an overall positive flux. And what does that say? If I have an overall positive flux, that means I must have a charge enclosed, and it is going to be positive. The same thing is over here. So if I look at this Gaussian surface that I drew just around the negative charge, I have overall a negative flux. Most of the field lines are piercing into this surface, which tells me I have a negative charge inside the surface. Now, this strange surface here, again, I didn't draw it very well, but I have some field lines piercing one way, some field lines piercing another. If I'd really paid careful attention and done this well, I would have seen, or I would have drawn, that the field lines all end up canceling each other out. So again, maybe look at the prettier visual in the PowerPoint, but overall, so it's a little hard to see the sloppy way I drew it on the board. Field lines into this surface are going to be equal to the field lines out of this surface. The net flux then is 0. Net flux 0 means there's no charge enclosed. And if we do the same thing for this larger surface, if I, again, drew it a little bit better, I have a certain number of field lines piercing out. I should have the same number of field lines piercing in. So although there's a lot going on in this large Gaussian surface, the total flux, the piercing out and then the piercing in, the total flux would be 0, which says my total charge enclosed is 0. So it doesn't mean I don't have charge in there. Obviously I have these two charges inside of this big surface. But if they're equal and opposite, the total charge enclosed is 0, right? So hypothetically, or maybe not hypothetically is not the word, but more theoretically, what Gauss's law allows us to do is, if we can figure this flux out, we can tell how much charge is enclosed. Or if we know how much charge is enclosed, we can figure out flux or even electric field. It's a nice way to find electric field if we have a more complex system than simple point charges. So another example with Gauss's law, and then we'll do 2 practice problems. Let's say that I have a single point charge, okay? I have a single point charge, and I am going to draw a surface to enclose this single point charge. Now, typically when you have just a single point charge, you always want to look for sort of symmetric surfaces. Again, I will explain what surfaces we use when as we power through these problems. So I'm going to choose a circle right here. If you're saying, why did she choose a circle? Just stick with me for now. So if this is a single point charge, I'm going to enclose it with a Gaussian surface. It would actually be a spherical shell. When I say circle, this is charge is a 3-dimensional thing. So this would be a 3-dimensional shell that I enclose the charge with, and I'm going to give it some hypothetical radius r, right? So if I use Gauss's law here, I can say epsilon naught times total flux is equal to charge enclosed. Total flux is electric field times surface area that field is piercing, and this is going to equal Q enclosed. So again, this is my little asterisk equation. This is the one we use most often. And so if I think about it, I didn't really give you anything here, but I said I'm surrounding this thing by a spherical shell. The surface area of a spherical shell is pi, no it's not. The surface area of a circle is pi r squared. The surface area of a sphere is 4 pi r squared. That is like something you learned, I hope, in geometry. And so if I go and put that in here, I can say epsilon naught times E times A, which is 4 pi r squared, that's the surface area of a sphere, is equal to Q enclosed. Now, this is not a specific problem, but just to make my point, I'm going to solve this thing for E, for electric field. So electric field is equal to Q enclosed over 4 pi epsilon naught r squared. I'm just rearranging that a little bit. So we could say 1 over 4 pi epsilon naught times Q over r squared. This is, I just proved, really, this is the electric field from a point charge. So if I'm a distance r away, my electric field is equal to 1 over 4 pi epsilon naught, or K is how I was writing that, times Q over r squared. So this proves, I'm using Gauss's law to prove an equation we've already been using. Now, I'm going to make a second video and come back to Gauss's law, and we're going to do 2 practice problems with it to hopefully make it a little bit more tangible. In total, just so you know, with Gauss's law, we're going to do, I don't even know how many, but like 7 or 8 different practice problems. So it'll be a lot. You'll have the homework sets really chunked out for you. So be patient with it. Right now, as you're finishing taking notes on this part of it, it should still feel quite abstract, I would imagine. All right, I'll be back with video 2.